Good morning, guys. Today what we're going to do is we're going to be talking about waves. We're going to go into some of the basics today. So we're going to talk about the two types of waves that exist. And this is universal. You find these everywhere. Light coming to the sun travels as a wave towards us. Sound that moves from someone's mouth to your ears, that moves as a wave. So we're going to learn a little bit about the types of waves. We're going to talk about how waves move from one place to another, the fact that some waves need something to move through. So, for instance, sound has to have something to move through, a medium we call this. And so sound will travel through air, but when you watch a movie and there's a big explosion in outer space, you're never going to hear it. Sound has to have something to move through, and in space, there's nothing. We're going to learn about kind of the geography of waves, some of the parts. And then we're going to talk about some of the waves that we experience in everyday life and just how big these things are. So we're going to go ahead and get started with a brief discussion of really what a wave is and more importantly, what a wave does, because every wave pretty much does the same thing. So the one thing that every wave is going to do, every wave is going to transmit energy. They move energy from one place to another place. So one example of waves that you're probably pretty familiar with would be water waves. If you go to the beach up in San Diego, you're going to see waves coming in off the ocean. And those waves are doing just what I'm saying here. They're transmitting energy from some storm where there was wind in that storm that generated that wave, and that wave is going to carry energy that storm had within it all the way to the coast of San Diego. Now, this storm could have been in the South Pacific somewhere, down south of Hawaii, thousands of miles away, but that wave form moved all the way to the coast of California and then dumped its energy on the shoreline there. Right? Tsunamis are extremely large, what we call pulse waves. And a tsunami also would transmit energy, the energy of the actual earthquake. So as I'm mentioning that, some other things we see maybe more frequently than a tsunami would be a radio tower, radio transmissions. So if you listen to a radio station, that radio station is going to transmit energy. Fact is, if you ever hear a radio station talking, it used to be the rule they had to state like how powerful they were. And so they transmit, their transmission is measured in watts. That's a measurement of power or energy per second. So for instance, if you listen to the radio here in Imperial Valley, one of the things you'll notice is that we hear, if you flip through the radio band, the stations, you'll find you hear a lot of stations from Mexicali and other places in Mexico. The reason why you hear some of that is they're allowed. There's an agency of the government that basically tells you, if you want to start a radio station, they say, here's the frequency. We'll learn more about these words as we go forward, but here's the frequency that you're going to broadcast at. Maybe it's 94.5 FM or 93.7 FM or 92.7 FM, or maybe you're in the AM portion of the frequency, 1230 KXO. Again, we'll talk about these different things as we move forward. They tell you what frequency you can broadcast at, but then they also tell you how much power you can broadcast with. So here in the United States, 50,000 watts is about as high as you can go. In Mexico, they have a higher maximum. So there are some companies, for instance, radio companies in the United States that do their broadcast, but then they actually send the signal out in Mexico because they have a permit that allows them to do it there with more power. That just means it goes further. Okay. Another example, as I was mentioning, earthquakes, earthquake waves. We just had a few earlier this week that some of you guys may have felt. That earthquake occurred kind of out past Sealy towards Ocotillo. That's where the actual energy was generated, but it traveled all the way to us so that you guys could feel it. It travels using a wave, okay? By the way, this picture right here, this is what was left over of the Imperial Water Tower. Way back in 1979, we had a big earthquake down here, and the energy that it transmitted was strong enough to knock over this tower. It basically demolished the thing. And we don't even have it. This one used to be behind Ben Hulse. Ben Hulse School is where our water plant for the city is, and this tower basically fell over during that time. Okay, so again, that energy is strong enough with an earthquake. It's strong enough to do some real damage, and it moves from one place to another using waves. So as we look at different types of waves, you can have two types of wave energy transfers. So one, you could get what we call a periodic wave. And what this would be, a periodic wave is a wave that consists of high points and low points, and it just keeps on coming. So again, if you go to the beach, you're going to see waves coming in one after another, and there's kind of a pattern to them. They come in every so many seconds. They're so far apart. There's just a repeatedness. Okay, there's a repetition that occurs with typical waves. Okay, on the other hand, you could get what's called a pulse wave. A tsunami, you guys, is an example of a pulse wave. It's a one-shot kind of a deal. It's an explosion. Any kind of an explosion would be a pulse wave. It's a one-shot, big high amplitude, and then it drops off. Okay, but it doesn't repeat. It doesn't keep coming. So pulse waves are a one-time surge of energy. Kind of, I'm giving you the example here. Kind of like, think about like you're trying to you're washing a car or something, and you're trying to pull your garden hose towards the car, but it gets caught on a rock or something. So what do you do to clear it? You kind of give it a one-time little flick of the hose, and that kind of makes that wave travel down the hose as kind of a bump, you could say. And as that bump gets to the barrier, it kind of jumps over it. That's a one-shot pulse wave is what that's called. Any explosion that you see is going to be a pulse wave. This picture that's shown here, this is an artist rendering of a place in Russia called Tunguska. And Tunguska in 1905 was a location where a large meteorite came into the atmosphere and then exploded above the ground. And when it did, so much energy was released by this pulse wave that left the explosion area, that all of the trees for like a 30 square mile area were all just snapped off right at the ground. That energy was so high, it just broke them off. It didn't uproot them, like usually when the wind blows hard, it will take a tree and sometimes it'll take the whole root ball and just turn the whole thing on its side. It snapped them off right at the ground. That's how sudden and violent that energy was. And so we have these two different types. Periodic waves, like the ones you see at the ocean, like the ones that your cell phone utilizes, are much more predictable. They repeat over and over again, which is good in terms of us using them for communications and things. We know what they're going to do. They're very predictable. A pulse wave oftentimes is not. Like I said, explosion, an earthquake, a tsunami that's created, this explosion that you get from an exploding meteorite, those kinds of things. All right, so these are two different types of waves that vary based upon whether or not they repeat. And my animation didn't like to work unless I just didn't animate it. So when we look at the two different types of waves, we can break them into two types also. One's called longitudinal, and the other's called transverse. Now, what I'm showing you on this screen is what is called a longitudinal wave. Sound is a good example of a longitudinal wave. All right. So what characterizes a longitudinal wave? When are you going to get a longitudinal wave? A longitudinal wave is going to have particles that vibrate, that move back and forth in a direction that's parallel to the direction that the wave is moving. Okay? So basically, you can see in all these little particles that are illustrated with the black dots, you can see there's a few red ones in there to kind of help you keep track of what they're doing. But I'm going to kind of put the cursor right about where this one is. And you can see that this red dot is just moving back and forth horizontally. Now, if you look at the wave itself, this wave is moving from left to right, also moving horizontally. So what I'm saying here is that the direction that an individual particle moves is parallel to, it's horizontal, and that's parallel to the direction the wave itself is moving, because that wave is moving basically towards the right from the left. So the wave's moving horizontally, and the particles are moving horizontally. Okay, hopefully this isn't hypnotizing you or anything. All right, so the point here is that if you look at the wave itself, I'll just kind of track the wave. Here's the wave. And that wave is slowly moving left to right, all the way across this space that's here. Okay? But the particles themselves, do individual particles move with this wave? Look at how this is going. Do individual particles actually move with the wave? Well, look at the red ones. Are those red ones moving with the wave as the wave goes all the way across this space? No. The wave, the energy moves, the waveform moves, but the particles that the wave moves through do not. They just oscillate back and forth. They basically go to the right a little bit, and then they snap back to the left. And there's a reason that they do that. And the main reason is that when you think of this area like that I'm pointing out right now, I tend to have more particles in that space, meaning they're more densely packed. There's more of them along that line. That means that's going to make a high pressure. And the area in between here, in between two high pressure areas, that's a low pressure. So if you think about this particle, it gets shoved into the high pressure area, but it would like to move back to the low pressure area. So that's why it kind of snaps back into that space in the middle and then gets caught up in the next high pressure. So just notice here that the way that this particle moves is parallel to the way that the wave itself is moving. Okay. On the other hand, if we look at the other type of wave, which is called a transverse wave, all right, a transverse wave has particles that vibrate in a direction that's perpendicular to the wave motion. So you can kind of watch this wave, and again, I'll kind of run the arrow through it. The cursor, I'll try to keep it on there. The cursor is moving left to right with that wave. This is kind of like a water wave. Water waves move like this. So again, that wave is going to move left to right, but try to focus on one individual particle. What direction are they moving in? Focus on one individual particle. Pick out one and just focus on it. As the wave is moving left to right, what direction are the individual particles moving in? Well, if you can see them, they're moving up and down. Those particles are basically just moving up and down while the waveform continues left to right. So what we would say is that the wave itself moves perpendicular to the direction that the particles are moving. okay? Particles up and down, waves moving left to right. And again, this is the way that water waves work. So if you've ever like been to the beach and you watch the surfers, they'll paddle out there on their board. And then when they get out past where the breakers are, a lot of times what they'll do is they'll just sit on their board. They get out of the water and sit on their board and dangle their feet in the water so they can be shark bait or something. But they sit there and they don't really have to paddle at all to stay where they're at. So the way to think about this is the water molecules are going to move up and down while the wave moves towards the shore. And this should kind of make sense to you. If the water itself moved towards the shore and not just the wave form, then you'd end up piling up lots of water right on the shore. And we don't see that. The water level on the shore pretty much stays the same all the time. So what that basically, that's because the water that's out there 100 feet offshore, it just stays there and moves up and down as waves come under them. You can even see it if you watch the surfers. If you watch those surfers, you can see them on their boards and they'll just kind of bob upward and then downward, up and then down as the waves go underneath them. But they don't really move in towards the beach anymore, okay? So longitudinal waves have particles that move parallel to the direction the wave's moving. Transverse waves, like this one, have particles that move up and down. They're perpendicular to the direction that the wave is moving. All right, something else you guys should know, you should be able to identify whether or not a wave is transverse or longitudinal. And you should know some of the parts of that wave. So this is kind of like, I call it like wave geography. You just kind of know what the parts are. So usually when we write a longitudinal wave, they're kind of hard to diagram because the particles are just moving this way and so is the wave itself. But usually when we diagram a longitudinal wave, we'll have some areas where we put lines or dots that are really close together, like you see here and here. And you'll see other areas in the wave, and it's usually halfway in between two of these areas where they're really close together. You'll have an area where they're really pretty far apart, okay? So we call these areas by different names. So this area that's really close together, I guess I do the transverse first. Actually, I'll go ahead and I'm gonna come back to this. The two ways that we label these, the areas where they're really packed closely together, we call those compressions. So the compression, this should kind of make sense. The compression is the area where the particles are compressed. They're squeezed together. All right, so that's a compression. This is a compression, okay? The areas in between the compression, so halfway in between these two compressions, I have an area where the particles are really not very much compressed. We call those by two names. One thing we can call it is an expansion, the area where the particles are pretty far apart. We call that an expansion. Or more oftentimes, we call it what's called a rarefaction. A rarefaction. That's R-A-R-E-F-A-C-T-I-O-N. Rarefaction. And again, that's going to be an area where the particles are spread out. And that rarefaction is always halfway between two compressions. Okay. If we look at a transverse wave, we usually label those like a typical wave that you would see. And we have some names for these. First, the peak here we call a crest. So that's a crest. This is a crest. All right. The low spots in the wave, in a transverse wave, are called troughs. So that's a trough. This is a trough. And notice that in the same way that you're going to get a compression, or I should say a rarefaction halfway between two compressions, you're going to get a trough halfway between two crests. Okay, it always works that way. Okay, so crest, trough, okay? They were wrong when they put this period on here, so I changed this. The distance between two successive troughs, so two troughs that are one trough and the one that's right next to it, that distance is called a wavelength. All right? And you could also measure from this crest to this crest, that distance, one wavelength. Okay? If I went from here, this spot right here, to the same spot on the next wave, which basically, think of it this way, this wave's coming up and gets to this middle part here, and it's coming up again and getting to that middle part here. So that would be a wavelength. If you measured this, or this, or this, you're going to get the same length for a particular wave. Okay, wavelength is like a constant for a wave. And then the other thing I would say, one other thing you should know, the height of this wave from this middle line, right? This middle line here, we call that the equilibrium position. The height from that point up to the top of the crest is called the amplitude, okay? You could also go from here down to the bottom of the trough. That should be the same exact distance from here to here as it is from here to here, and we call them amplitudes. Now, if you think about the amount of energy that a wave carries, amplitude has a lot to do with it. If you've ever been to the beach when the waves are 6 feet high, all right, if they're 6 feet high, you know that wave is going to have a lot more energy in it than if the waves are only 2 feet high. So the amplitude tells you how much energy that this thing is really capable of carrying. All right, you know if you've been in 6-foot waves because they pound you. You get pushed all over the place, you get thrown under the water, like ran against the sand and that kind of thing. It's not pleasant. So the amplitude tells you how much energy that they carry. It really has not a whole lot to do with like radios though. Okay, so those are things you guys should know. You should be able to identify amplitude, crest, trough, wavelength. You should be able to identify a rarefaction or an expansion, same thing, and a compression in a longitudinal wave. You should also be able to look at one of these two diagrams and be able to tell me, is it longitudinal? Is it transverse? Okay, just remember, transverse always looks like kind of a snake or something. Longitudinal always has a straight line kind of a deal. Okay, moving on. So some other things that you should know, and you really can't show this on a diagram, but you should know what frequency is. Frequency, if you think about, if I were to use frequency, I'd be talking about how often something happens. So for instance, if I get a newspaper every day, then I would say that the frequency that I get the newspaper would be once a day. Okay? So basically, if we talk about frequency in terms of a wave, this is basically the number of wave crests that seem to pass a particular point in a certain amount of time. Okay, so for instance, if I'll go way back here to the screen that had I'll go back to the longitudinal one. It's a little bit easier to see. So basically what I would say is I want to know how many waves pass a particular point in a certain amount of time. So if I counted, there's like 1, 2, 3, 4. So if I counted the number of waves that got to the end of this point, let's say that I got 20 in a second, I would say that my frequency would be 20 waves per second. Okay? So that's all that frequency is. Frequency is simply a measurement of how many waves that you get that will pass a particular point in a certain amount of time. And that usually is per second, is what I would say. Okay? So frequency is the number of waves that pass a certain point in a second. And what we usually measure this in, the units that we usually use units of hertz. So you may hear hertz or kilohertz or megahertz. Your cell phones typically operate in the gigahertz range. 1 hertz, which is abbreviated capital H, lowercase z, is 1 wave per second. Okay? Do you think in the ocean you're seeing a frequency of water waves that are 1 hertz? Do you think you're getting a wave each second? If you were in the ocean and you were getting a wave each second, it would really be beating you up. I would say that typically when you're at the beach, you're going to see a frequency of water waves that's somewhere in the neighborhood, probably of, I don't know, maybe instead of 1 wave per second, it's probably more like 10 seconds for each wave. Okay, there's a delay in between each one. Okay, but the typical unit that we use to measure hertz, and you'll see how I do this in a minute here, would be, or to measure frequency is hertz, which would be 1 hertz, 1 wave per second. So if you had 10 hertz, that'd be 10 waves per second. All right. Also, a variable of waves is how fast they move. So we also have what's called wave speed, and this is just what it sounds like. It basically tells you how fast that a wave moves through the medium that it moves through. Okay, and there's a relationship between wave speed and frequency, and it basically goes wave speed equals frequency, that's how often the waves basically come, times the wavelength of the wave that we talked about a couple of slides ago. So how long the wave is, that's the wavelength, times how many waves per second go past you. This is going to give you the wave speed. And this is true for every kind of wave, whether it's sound, whether it's light, whether it's radio signals, whether it's your cell phone or your wireless internet at home or your Bluetooth. This relationship is true for every single wave that you will find. All right? Wave speed equals frequency times wavelength, or if we use variables that are commonly used with waves, v, velocity, equals f, frequency, times lambda. And this lambda is what this is. It basically is the variable used for wavelength. Okay? And one wave speed that you guys should know, okay, is the speed at which light moves, because there are a lot of different types of waves that move at light speed, okay? A lot of different waves that move at light speed. And so you guys should know this value that's down here. You should write it down somewhere. Basically, all waves, all light waves, travel at 3.0 times 10 to the 8 meters per second. This is, what would this be? 300 million meters per second is how fast this is. Light is very, very fast. Actually, typically in class, we'll figure out how fast this is in miles per hour, because Americans aren't too good with meters per second. And if I remember right, the quantity, when we figure this out, it's 571 million miles, okay, 571 million miles per second, all right, 571 million miles per second. Very, very, very fast is what we would say. Okay. So what travels at that speed? The light that you use to see travels at that speed. Radio waves, your cell phones, radio stations, X-rays, if you've ever broken a bone or had to have an X-ray, they move at that speed. Okay, any form of what we call electromagnetic radiation or electromagnetic waves travel at this speed. Now, what I'm going to do now, yeah, I'm going to come back to this the next time. But what I'm going to do now is I want to talk about this relationship between wave speed, wavelength, and frequency by looking at or thinking about a few things that we use waves for. So for instance, if we look at radio stations, now I'm trying to remember the radio station you guys typically listen, if you listen to radio stations, not many people do anymore, but there's a radio station down here, I think it's 92.7 is what the frequency is, and that's FM. Now, if you ever listen to the radio in the car, if you're listening to the FM, that frequency is actually measured in megahertz or MHz. Now the prefix mega, anytime you see a prefix mega, mega is a million, is what it is. So that would basically be megahertz. 1 megahertz would be a million hertz. So if I have 92.7 megahertz, that would be 92,700,000 hertz. So if you think about this, every single minute of every single day, you guys, you're getting hit by a crest from this radio station. You get hit by that crest 92,700,000 times a second. You guys are getting hit by that station right now. Okay? Why don't we notice it? Well, radio waves tend not to carry a ton of energy. That's part of it. Okay? Let me make this a little bit bigger on the screen. I hope you guys are seeing it fairly large. Yeah, so 92,700,000 times every day, actually not every day, every second, you guys are hit by a wave from this station. So my question is, how big is this wave? How large is it? Well, I can use our relationship that we just had, which was the wave speed equals frequency, or F, times lambda, or wavelength. What we have right here, you guys, this is our frequency. Okay, what I would like to know is how big's the wave? So I can do just a little bit of algebra here, and I'll say that the wavelength, how big the wave is, to isolate that, I would just divide both sides by frequency. So I would get wave speed, the velocity, or V, over the frequency. All right? So the advantage that we have is we know what radio station velocities are. It's whatever light speed is. So it would be 3.0 times 10 to the 8 meters per second. I just gave you guys that on the last slide. And what's the frequency? It's 92,700,000 hertz. Or you know what I'm going to do? Instead of writing hertz, let's call it waves per second, just because it makes our units work a little bit better. Now, if I were to cancel out my units, the seconds here would cancel the seconds here. They're both in the denominator on opposite sides of the fraction bar. So the unit I would be left with would be meters per wave. Well, that is essentially wavelength. Wavelength is going to be measured in meters. So all I have to do is divide this number by that number. Let me get the calculator out. Actually, I'm using my cell phone, so hopefully it lets me do the scientific notation. So this is 3.0. And I'm going to do enter exponent 8 equals, okay, that did it right. Now I'm dividing by 92,700,000. And this gives me 3.24 meters. So to give you guys a perspective, you guys are probably, well, most all of you guys are a little less than a meter and a half or so. It's about how high you guys are. Your ceiling, you guys, or actually no, even a better one, think about a basketball hoop. A basketball hoop is just about 3 meters above the ground. So from the ground to a basketball hoop, that's about how big that wave is. And it's hitting you. A crest from that wave is hitting you 92,700,000 times each and every second. Okay? Now, on the other hand, if I look at an AM radio station, like KXO in El Centro, their frequency is 1230. Now, they're kilohertz, not megahertz. So this basically would work out to, this is 1,000 hertz. So I would just multiply this by 1,000. I'd get 1230 and then just add 3 zeros. That's multiplying by 1,000. So that means you're getting hit, basically, you're getting hit 1,230,000 times a second by this wave. So if you notice these two numbers, okay, I'm getting hit almost 100 times more every second from this FM wave than I am from this AM wave. So if we can calculate that, basically using the same formula, we can calculate that wavelength's length using that same relationship. It still travels at 3.0 times 10 to the 8 meters per second. But the frequency now, instead of being 92,700,000, our frequency now is 1,230,000 waves per second. So what that means, because I'm dividing by a smaller number, I'm going to get a bigger wave. Okay? So I'll go ahead and do that. Okay, so this is 3.0 and our exponent 8 equals divided by 1,230,000 equals. This wave, you guys, where this one was 3 meters long, about the height of the basketball hoop, this is 244 meters long, okay? Meters per wave, or just meters. So to put this into perspective, if you were on the football field at the high school and you started on the north end, that's the end that's towards the baseball field, and you went all the way across the football field, you would go across Barione Boulevard and probably just beyond the fence at Ben Hulse would give you 244 meters. This is a way bigger wave. Now, here's why I do this and why it's important, you guys. Each one of the crests from these waves, so each crest, each trough in these waves is an opportunity to send you information. So I want you to think about what you hear on FM radio. What you hear on FM radio is typically music. What do you typically hear in AM radio? Well, in AM radio, you usually hear like talk shows, sports, that kind of stuff. You don't usually hear a lot of music anymore on AM radio. Well, why would this be? If you think about this, there's one thing you get with FM that you can't get with AM, and that is stereo. You guys may know what stereo is, hopefully. Stereo is when, like, if you're listening to music and you hear drums on one side, if you have your headphones in, you know what I'm talking about. Like the drums in music will come in on one side, like in your right ear, you'll hear it. And then in your left ear, you're going to hear guitar come in or the bass come in, or you'll hear different channels essentially on left and right. That's what stereo is. And because of the fact that these waves are shorter, these FM waves are shorter, a lot shorter, I'm going to have almost, you look at the difference, it's almost 100 times, this is almost 100 times bigger, which means I get 100 times fewer waves from AM, and I get more chances from FM since I'm getting hit by these a lot more frequently. So this FM, I get hit so frequently with these waves, they actually have enough space that they can do two different channels at the same time, a left and a right. I can't do that with AM. You hear the same thing through both speakers when you listen to AM, okay? Because of the fact I don't have the ability to transmit information, okay? If I look at your cell phones, you guys, I'm going to kind of wrap up with this. Your cell phones, if you have 4G, it's 1900 megahertz, or 1900, and then meg is a million. I'm just going to add 6 zeros. So basically, if you have 4G, you're getting hit 1,900,000,000 times a second is what you're getting. And I think I figured this out before. This comes out to about 28 centimeters, I think is what it was, per wave. So while this one's like 1.5 football fields, this one's about as tall as a basketball rim is off the ground. This one's 28 centimeters is going to be about 10 inches, which is just about, if I pull back here, it's just about the distance from the bottom of the page to the top of the page. So you're going to have a crest here, goes down to a trough here, and then back up to a crest at the top of the page. Now, why would I want such a big wave or such a short wave for my cell phone? Well, remember, if you're looking at this wave and it looks like this, the tighter that those waves are, the tighter those crests are, the shorter the wavelength is, the more opportunities you're going to get to transmit information. So essentially, you guys, until you got high frequency cell phone signals, you couldn't have internet on your phone because you couldn't transmit the information back and forth fast enough. If you think about a phone, what does it do that a radio doesn't do? Phones allow for two-way communication. I need a lot more chances to transmit information if I'm going to have that. If you look at 5G, what are they doing with 5G? Well, this is gigahertz. Giga is a billion. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9. That's a billion right there. So while 4G does 1.9 billion waves per second, this does 28 billion waves per second. Okay, roughly what, 15 times what this does. Well, that means you get 15 times more chances to transmit information, right? This is why frequency is important. This is why you pay extra money if you're going to have a 5G network, because it's more capable than a 4G is. Okay? All right, you guys, I'm going to stop right there. Now, this relationship that you saw me use right here, you guys are going to get some problems that you're going to work on. So I want you to figure them out. I want you to show the work that I showed. So I want to see you plugging these values in with units like I did here if you want to get full credit on these, okay? So you will see that show up on your on your modules page after you guys get done watching this video. All right, I'm going to end it right there, you guys. I hope you have a great rest of your day, and I will see you next time. Bye-bye.